Hello everyone. Now we have to discuss the next concept, that is coupled circuits, analysis of coupled circuits. So what is the meaning of this coupled circuits? Means we have to analyze the interconnected loops of an electrical network through magnetic field. So if we are dealing with the magnetic field, that is called coupled circuits. Okay. In this we have to discuss self and mutual inductance and coefficient of coupling. First, before that, analyzing the interconnected loops of an electrical network through magnetic field. Through magnetic field is called coupled circuit. That's it. So in this, first we have to discuss self inductance. Self inductance. What is meant by self inductance? Before that, let us have a core. So in that core we are having a winding. Yeah, this is the winding, and the current through this winding is, for example, I, right? So entering is I, leaving is I. Therefore I, this is I. Okay. Therefore, when the current through the conductor, obviously what will have? A flux is developed in the core. See how we can get the flux. See this, if the current represents the orientation of fingers, then the flux represents thumb, right? If the current represents the orientation of fingers of a hand, obviously the thumb represents the direction of flux. So here the orientation of fingers upwards, right? Obviously the thumb represents what? Left side. Like this we are having the flux, direction of flux is like this, right? For example, if we have another conductor, in that also we are having current. Let us say that, yeah, like this. The current entering from another end, okay, and leaving from this end. Then what about the direction of the flux? In this case it is from left to right, right? So in the first case it is from right to left, but in this case it is from left to right. So current represents what? Orientation of fingers, and thumb represents the direction of flux, right? Then what about self inductance? that is, when a current changes in a circuit, the magnetic flux linking the same circuit changes. Because the current in this circuit changes, obviously the flux which is present in the same circuit also changes, right? That is nothing but self inductance. If current changes, flux changes, obviously an EMF will be induced. When a current changes in a circuit, the magnetic flux linking the same circuit also changes. Vice versa. Vice versa means what? If flux changes in the circuit, obviously the current in the same circuit also changes, and EMF will be induced in the same circuit. That's it. This is about self inductance. Then the induced EMF is always proportional to the rate of change of current. The induced EMF is always proportional to the rate of change of current. That is, what is the induced EMF? Let us say V, which is proportional to what? Rate of change of current, di by dt, right? So in order to eliminate this proportionality, we have to introduce some term, that is L. Now it is V is equals to L into di by dt, where V is what? This is induced EMF. This is what? Self inductance, which is nothing but constant of proportionality, right? And this is what? Rate of change of current. That's it. Then however, we all know that L is equals to N into d phi by I, right? That is, where N is equals to what? Number of turns. Phi is equals to what? Flux linkage, right? Flux linkage. Here L is equals to N phi by I. Therefore, from this I is equals to what? N phi by L. Then substitute this value of I into this equation. Therefore, P, which is equals to L into, in place of I, we have to write N phi by L by dt, right? Which is equals to what? L into 1 by L into N into d phi by dt, which is equals to what? V is equals to N into d phi by dt. This is, let us say, and this is, let us say, this is 1, like that. This is 2. From 1 and 2, what is that? L into di by dt, which is equals to N into d phi by dt. Dt gets cancelled. Therefore, what we have? L is equals to, which is equals to N d phi by di. That's it, right? This is what? Self inductance. This is for self inductance. Then what about mutual inductance? So coming to self inductance, if the amount of current is changes in the circuit, obviously the flux in the same circuit also changes. That is called self inductance. So coming to mutual inductance, what is the meaning? If the amount of current is changes in one circuit, then the corresponding flux is changes in another circuit. Therefore an EMF will be induced in the another circuit. So current changes in one circuit, but an EMF will be induced in the another circuit. That is called mutual inductance. Now we have to discuss that mutual inductance. For this mutual inductance, this is the circuit. Okay, the current through this I1, like that, this is I2, and this is P1 AC, this is load, let us say. Okay, load. So the flux linking in the circuit 1 is, for example, phi 1, this is phi 2, right? See, the current representation is what? The orientation of finger represents what? Current. Obviously this is what? Flux direction. This is what? This direction, right? In this we have downward direction. That's it. Then what about mutual flux? What about this is mutual flux, that is phi 1 2, which is equal to phi 2 1. Let us assume both are equal. Okay, so phi 1 phi 2 are nothing but what? A leakage flux of coil 1 and coil 2, like that. Phi 1 2 phi 2 1 are nothing but mutual flux. So we can write here I1 nothing but currents in the coils, those are nothing but alternating, right? Next, phi 1 and phi 2 are nothing but leakage flux in coil 1 and coil 2. What about phi 1 2 and phi 2 1, which is nothing but mutual flux. Next we have number of turns, N1 and N2 are nothing but what? Number of turns in coil 1 and coil 2. That's it. So the induced voltage in coil 2 is due to what? Rate of change of flux linkages in coil 1. That is mutual inductance. induced voltage in coil 2 is due to rate of change of flux linkages in coil 1. That is nothing but mutual inductance, vice versa. Therefore, what we have? V1, or we can write VL1, which is equals to B, because we have two circuits, right? N1 into di1 by dt. Sorry, rate of change of flux linkage, right? Rate of change of flux linkages, that is mutual flux, right? That is, we can write d521. The voltage in coil 1 is due to what? Rate of change of flux linkages in coil 2, like that. The voltage in second circuit should be equals to N2 into rate of change of flux linkages in coil 1. That's it. This is set of equation 1. Here 512 is nothing but what? Related no need. Or we can write induced voltage in coil 2 is due to rate of change of current in coil 1, right? You can write like that. The induced voltage in coil 2 is due to rate of change of current in coil 1. That is vice versa. So from this, PL1, which is equals to M into di2 by dt, and PL2, which is equals to M into di1 by dt. What is this before that? You can write proportional to di2 by dt. The voltage in coil 2 is due to what? Rate of change of current in coil 1, vice versa. Therefore, to eliminate this constant of proportionality, PL1 we can write M into di2 by dt, like that. VL2, which is equals to what? M into di1 by dt. These are second set of equations. So, where M, which is equals to constant of proportionality called mutual inductance, right? Therefore, from 1 and 2, we can write, let us say, M into di1 by dt, which is equals to N2 into d512 by dt, N2 into d512 by dt, or you can consider m into di2 by dt, n1 into d521 by dt, whatever it is. Okay, from this m, which is equals to what, n2 d512 by di1, right? d5 by I, simply inductance, whether it is self or mutual inductance, n5 by I, right? Like that. Similarly, for second case also, m which is equals to n1 into d51 by di2, right? Sorry, 521. This is 521. That's it. This is another set of equation. So here the mutual inductance is the bilateral property of the linked coils. So mutual inductance here is that the bilateral property of linked coils. That's all for mutual inductance. What is self inductance? The rate of change of current is there. Obviously, there is a flux developed in the same circuit. Obviously, what about mutual inductance? If the rate of change of current is there in one circuit, we are having the induced EMF in the another circuit, vice versa. This is about self inductance, mutual inductance. Now we have to discuss coefficient of coupling. So what is meant by coefficient of coupling? It is defined as the fraction of total flux that links the coil. For example, total flux is nothing but phi 1 or phi 2 with respect to coil 1 or coil 2. So phi 1 2 is or phi 2 1 is nothing but mutual flux. So in that, how much fraction of mutual flux is there from that total flux? That is nothing but coefficient of coupling. So you can write, it is the fraction of total flux that links the coil. That's it. So coefficient of coupling we can define with K, which is equals to what now, phi 1 2 by phi 1, which is equals to phi 2 1 by phi 2, right? So phi 1 is the total flux in coil 1, phi 2 is nothing but total flux in coil 2. So how much fraction of flux which is present, that is phi 1 2 from this phi 1, like that how much fraction of phi 2 1 is present from this phi 2, that is nothing but coefficient of coupling. Where phi 1 2 phi 2 1 are what, mutual flux, like that phi 1 or phi 2 are nothing but self flux or leakage flux. Next, obviously phi 1 2 phi 1 and phi 2 1 less than phi 2. Hence maximum value of K is unity. Hence . is what? Unity. Let us say phi 1 2 which is equals to k into phi 1 and phi 2 1 which is equal to k into phi 2, like that, right? So maximum value is nothing but unity only. If k is less than 1, k which is equals to 1, k which is more than 1, what is that meaning? If k is less than 1, that is called under coupling. This is most practical, right? If k is equals to 1, that is ideal coupling. If k is more than 1, that is over coupling. This is impractical, right? The range of k is nothing but always therefore range of k is always less than or equal to 1. Always less than or equal to 1. That's it. This is coefficient of coupling. So we know that m which is equals to, let us say, second coil N2 into d phi 1 by dt and m which is equals to N1 d phi 2 by dt, right? The rate of change of flux due to second coil in coil 1 due to second coil, the rate of change of flux in coil 2 is due to what? Current in first coil. So this is due to coil 2, this is due to coil 1. So for example, if you multiply these two, let us say this is 1, this is 2, 1 into 2 which is equals to what? M square, which is equals to N1 N2 phi 21 into phi 12 by N phi 1 by, sorry, I1, right? We can write M equals to N into phi 12 by phi 1. This is what? I1. Yeah, this is what? Phi 21 to I2. Okay. Now it is what? Phi 12 into phi 21 by I1 into I2. That's it. Therefore, M square which is equals to N1 into N2. In place of phi 21, we have to substitute k into phi 1, like that, k into phi 2 by I1 I2, right? Therefore, M square which is equals to N1 N2 into k square phi 1 phi 2 by I1 I2, I1 I2. Now we can write M square which is equals to k square N1 phi 1 by I1, like that, N2 phi 2 by I2, right? So from this m square which is equals to k square, this is L1, this is L2, because L1 is what? N phi by I. Simply self inductance is nothing but N phi by I. Therefore m which is equals to k into square root of L1 L2, right? From this k which is equals to m by square root of L1 L2. So this is the formula for coefficient of coupling. Coefficient of coupling. For ideal case, m which is equals to what? L1 L2, right? Because k is equals to 1, since k is equals to 1. So here m is what? Mutual inductance, k is coefficient of coupling, L1 is self inductance of coil 1. You can write here k is equals to m by L1 L2, right? Where k is equals to coefficient of coupling, m which is equals to what? Mutual inductance, L is nothing but self inductance of coil 1, like that L2 which is what? Self inductance of coil 2. That's all for self inductance, mutual inductance and coefficient of coupling. Here we can write for ideal case k which is equals to 1. Therefore m which is equals to L1 L2, that is what? M square minus L1 L2 which is equals to 0. If L1 which is equals to L which is equals to L, if for example self inductance of coil 1 and coil 2 are equal, therefore what about this condition? Therefore m square minus L square which is equals to 0. At that case mutual inductance is equals to self inductance. That's it. Mutual inductance which is equals to self inductance. These are very, very important observations, right? So from this we can write m square which is equals to L1 L2. This is also one of the important observation. Okay, that's it.